This tutorial is about numerical integration using the rectangular method, which is the simplest of all methods. And in this tutorial, what we are primarily trying to do is we are trying to convert the um, integral into a summation where we divide the whole domain into small intervals. And as an example, we'll be integrating a simple function which is 12 plus 2 sine x minus x squared over 10. We have used this in our previous labs. It is primarily a shifted parabola on which a sine wave is riding. And if you integrate this, which is quite simple, using the exact method, you will find out that the answer is 173.33333, which we will be using to compare with our um, our numerical solution. So the first set of um, the rectangular method is a Newton-Cotes method in which the whole domain is divided into small rectangles, just like the Riemann sum. And so we basically just take the value of the function at a point and multiply it with the interval, and then we add many rectangles like that. So let's start the MATLAB code, and here I have already defined some variables. So here's the function. This is our 12 plus 2 sine x minus x squared over 10, and a and b are the limits over which we try to integrate. Now at this point I'd like to teach a function called integral in MATLAB, and of course this is doing numerical integration, but it's good to see that it's very well optimized method in MATLAB to perform numerical integration, and we will use its result to see what we get. And you can see it gives us 173.33, which we saw was the analytical solution. So we can treat this as the analytical solution. Now, in order to get numerical solution, we divide our domain into small intervals, and let's say that interval size is 2 units. So from minus 10 to 10, we can create the x values at which we are trying to find our solution, and you can see it will compute the value of the function at 10, minus 10, minus 8, minus 6, minus 4, all the way to 10, separated by 2 units along x-axis. And now we can find the value of the function at these points. So this will give us the corresponding y values at these locations. So you can quickly plot this using EasyPlot, and you should remember what it looks like. And now we can put these other values on it, the discretized points. So what we are trying to do is we have the value of the function at minus 10, minus 8, minus 6, and we treat this minus 10 as a constant value over the interval, and then this rectangle is the integral from minus 10 to minus 8, and we add these rectangles to get the integral under the whole function. And in order to do that, we basically run a for loop. Our n is, in this case, is 11. So we have 11 rectangles that we need to add together. And we start by saying that our numerical integral is 0. And then after each iteration, we add one rectangle to it. So let's say if k is equal to 1, which is this rectangle, we say in is equal to in plus dx, which is 2, times the yk, which is the first value. So y of k is 3.088. So 3.088 times 2 is added to in this little part. And then when the next part of the loop comes, k is equal to 2, in gets updated, where this portion plus this portion. So I'm going to reset in is equal to 0 and run the whole loop instead of going through each value one by one, and you can see that it's 174.17. So now you can display both the analytical value and the numerical value and see that what kind of difference we are getting. Now we can run this whole code and see the value, and now let's reduce the width to 1, the interval size, and you can see as you reduce the width, you get a little bit better result. Let's reduce it to 0.5, and you can see you get even a little bit better result. And this is what the rectangular method is for computing integral.